3.9 is about applications of the derivative. So we're given a multi-part question here. It's actually number 2 from the book. A particle moves along a line. For t greater than or equal to 0, the position of the particle is given by s, and t is measured in seconds, where s is measured in feet. Part A, find the velocity at time t. So the velocity is the same as the first derivative of f. I'm going to do the quotient rule. Low times the derivative of high would be 9 times t squared plus 9 minus high d low. High is 9t, and the derivative of the low is 2t, or the derivative of the denominator. And then we're going to square the denominator. That's low d high minus high d low over the bottom squared, and away we go. I'll just clean that up for the answer. Part B, find the velocity at time equals 1. So that means I'm going to find v of 1. Part C is asking me to find all times t when the particle is at rest. The particle is at rest when velocity equals 0. So I want to solve when v equals 0. That would be the same as solving for when the numerator equals 0. Divide by 9. The answer is t equals 3 seconds, because remember, t has to be greater than or equal to 0. Part D, the particle is moving in a positive direction when velocity is positive. So let's find when this is positive. Now the denominator is always positive. The denominator is t squared plus 9, quantity squared. That will always be positive. Factoring out the 9 and factoring further, when I'm solving an inequality like this, a quadratic inequality, I factor it down and I place the zeros on a number line, -3, +3, and then I can check the intervals. Obviously, we're solving for t here, so we really don't care about -3. We actually want to be thinking about values greater than or equal to 0 for t. So we can look between 0 and 3. In between 0 and 3 is the number 1. And if I go back to my inequality and I plug in 1, I'll get 9 times a positive is positive. So it would be positive in between 0 and 3. And then if I try a number greater than 3, like 4, I'll get 9 times a positive times a negative, which will be negative. So the values of t for which this inequality is positive are between 0 and 3. That will not include 3 because it just asked when it's greater than 0. So our answer is just 0 to 3, not including 3. Negative direction is when velocity is negative. So negative direction when v is less than 0. From our number line, you could see that is when t is greater than 3. Part E, find the total distance traveled by the particle during the first 6 seconds. We know that it was headed in the positive direction from 0 to 3. So I'm going to check f of 3 minus f of 0. That's the change in the direction. I'm just subtracting the 2. F of 3 is going to be 9 times 3 over 3 squared plus 9. 27 over 18 is 1.5. F of 0 is going to be 0. So 1.5 minus 0 is 1.5. And that is a unit of feet. Negative direction, we know, happened from our last response when t is greater than 3. And they said up until t equals 6 in letter E for the first 6 seconds. So we're going to find f of 6 minus f of 3. And we want the total distance traveled. So when we go to find f of 6, we're going to substitute that into f. So we'll get 9 times 6 over 6 squared plus 9. Now we know f of 3 already, so 1.2 minus f of 3 was 1.5. And this is a total distance traveled. So we're going to take the absolute value of this difference because we want the total distance traveled. Right here, total distance. So that means you're going to take an absolute value, and that's 0.3 feet. Letter F, we're going to draw a diagram to represent the motion of the particle. So we'll start by getting our time set up. Here's time 0, which is also where the particle starts, so that's the same as position is 0. And we'll go down to 3 because that's as far as it goes in the positive direction. So our particle is going to go down this way in the positive direction until t equals 3. And we know that it has gone 1.5 feet. So at t equals 3, we have s is 1.5. And then we need to comes back. So at t equals 6, we know now that the position is going to be a 1.2. Okay, that was calculated up here. So there's a diagram for the motion. The acceleration is going to be the derivative of velocity. So that means we're going to use a quotient rule. So we're going to do low d high. Low is our t squared plus 9 quantity squared, and the derivative of the high, or derivative of the numerator, is negative 18t minus high d low. So the high is 81 minus 9t squared. And the derivative of the denominator, I'm going to have to do the power rule first. So that'll be 2 times t squared plus 9. And then chain rule, I have to take the derivative of t squared plus 9 because that's the inner function. So that will be 2t all over the denominator squared. So the denominator was t squared plus 9 squared. So now that'll be t squared plus 9 to the 4th. And now I'm going to do algebra to simplify this expression. I'm noticing I have a t squared plus 9 in the numerator for both terms. So I'm going to start by factoring that out because I know I can cancel it with the bottom. So take out a t squared take out a t squared plus 9 from the numerator. That leaves negative 18t in the front, and then in the back that leaves a 4t. So I'm going to multiply this 2 times this 2t. So I'll have a 4t times 81 minus 9t squared, still all over this t squared plus 9 to the 4th. And I could cancel one of those right now. So I'm going to cancel. I'm going to use the calculator to evaluate a of 1 because we need the acceleration at t equals 1 second. And using my graphing calculator, I'm going to get about negative 0.306 feet per second squared. Part H, I'm going to have to graph the position, velocity, and acceleration for t is between 0 and 6. So you can use your graphing calculator to do this. I can enter in those derivatives into the graphing calculator. I strongly suggest you put f into y sub 1, which is 9t over t squared plus 9. And then in y sub 2, you take the first derivative, and in y sub 3, you take the second derivative. And then you can look at the graph. Graph will have the original position function, s, the velocity function. Remember, we know the particle's going to change directions at 3. So velocity starts off positive, and then it goes underneath the x-axis. And then acceleration, speeding up, means you are looking for when velocity and acceleration have the same sign. So that means when they're both positive or when they're both negative. The particle is slowing down when they have opposite sign. So obviously they have opposite signs up to 3. So we're going to start with 0 to 3, and then once the acceleration graph crosses over the x-axis, now it's positive while velocity is negative. So that would be t is greater than or equal to 5.196. If you calculated that by hand, that's the same as 3 root 3. The velocity function of a particle is shown where t is measured in seconds. When is the particle speeding up? The particle is speeding up when velocity and acceleration have the same signs. So if this is the graph of velocity, acceleration is going to be the slope of the tangent line to this curve. So from 0 all the way to 3, the slope of the tangent line would be positive. So A is positive right here between 0 and 3. And then from 3 to 4, A would be negative because the slope of the tangent lines to the curve would be negative. And then we have A is positive from 4 to 5. From about here, this is about 1 1/4, I would say. The 1 1/4 to 3 is going to be where A and V, or acceleration and velocity, have the same sign. So velocity is positive from 1 1/4 to 3. And then again, they have the same sign where A is positive again between 4 and 5. So 4 and 5 are the other times when the particle is speeding up. Okay, slowing down, they would have the opposite signs. So when do velocity and acceleration have the opposite signs? That would be between 3 and 4 because velocity is positive and acceleration is negative. Another application of derivative would be projectile. So in number 8, we have a ball thrown vertically upward with initial velocity of 80 feet per second. Its height after t seconds is given by s. What is the maximum height reached by the ball? In part A, the ball would reach a maximum height when velocity equals 0. Let's find the velocity first of all. The velocity is the derivative of position. The derivative of position is 80 minus 32t. So that's our velocity function. And we're going to set that equal to 0. So we have t equals 2.5 seconds. Now we need to know the maximum height. So go back to the position function and substitute in 2.5. So let's evaluate for 2.5. That would be 100 feet. Part B. What is the velocity when it is 96 feet above the ground on its way up, and then 96 feet above the ground on its way down? This means we want to set the position function equal to 96. So set that equal to 96 and solve. So I'm getting possible values of t as 2 and 3. That means I can substitute 2 back into the velocity function, and I'll get, which is 16 feet per second. And then again, the velocity is 96 at t equals 3. That is negative 16 feet per second because the direction is downward. Okay, I chose to look at current as another application of derivative. Your teacher may not have chosen this topic, so you could stop the video if your teacher did not choose this topic. Delta Q is the net charge that passes through a surface during a time period delta T. The average current during this time interval is defined as average current, or delta Q over delta T. The limit of this average current over smaller and smaller time intervals is the current I at a given time, T sub 1. So I is going to be the limit as delta T approaches 0 because it's just said it's over smaller and smaller time intervals. Therefore, the current is the rate at which the charge flows through a surface. The unit for this is amps, and it's denoted with an A. So the quantity of charge Q through a point in a wire up to t seconds is given by Q. Find the current when t equals a half, and then find the current when t equals 1. And then we'll have to find out when the current is its lowest. So here we go. The current is q prime. So let's take the derivative of q. So for part A, I'm going to evaluate q prime of 1/2. I end up getting 6. And you could put an A there. Q of 1 is going to give me 12 amps. At what time is the current its lowest? The current is lowest when Q prime has a minimum. So we are trying to minimize Q prime. That means we're going to take a second derivative. The first derivative was 12t squared minus 6t plus 6. So the derivative of that is 24t minus 6. If we take 24t minus 6, set it equal to 0, that means when t is 1/4, I can look at before 1/4. So let's say I look at 0. If I test 0 to the left of 1/4, I would get a negative in this derivative. So it'll be negative on the left. Now if I check a number to the right of 1/4, like a 1, if I try a 1 into this derivative, I'll get 24 minus 6, which is a positive number. So that means the graph of Q double prime is going from negative to positive. That means we have a minimum when t is 1/4. The current is lowest at t equals 1/4.